Of God. Hi everyone. My presentation is about the role of modified gravity model, especially the logarithmic form, in the structure of gravity's rainbow. Therefore, I will first give an elementary explanation of the background and motivation, then I will describe the calculation and the result of our work. So, recently many researchers believe that the cosmic inflation pattern is theoretically the best model for the universe. There is recently a vast effort to detect the signature of inflation on the CMB. Theoretical cosmology within London called dark matter physics needed an inflation period shortly after the Big Bang and to draw a consistent picture of the first phase of the universe and produce the universe observed today. Einstein's theory of gravity is valid for low energy, so Einstein's theory must be modified for high energy. As we know, the simplest form for gravitational theory is the modifier of our gravitational model, which is considered according to Einstein-Hilbert action. In summary, in the case of modifier of our gravitational model, a series of simplifications have been well studied in previous works. There are several approaches to have a quantum gravity in the corresponding theory. On the other hand, the gravity rainbow are formed by modifying the usual dispersion relation in the UV limit. Generally, one can say that we give some modification to the corresponding limit, which is related to the rainbow universe and they depend on the energy to the probe particle. Rainbow gravity constitutes a generalization to general relativity. In fact, in their theory, the spacetime metric felt by a free particle depend on the pure particle energy or momentum. Therefore, spacetime is determined by a family of metric parameterization by the probe energy in form of the metric rainbow, called gravity's rainbow. The method and formulas associated with the rainbow universe have been used in many works in recent years, and various models have been studied using the modified Friedman equation. In the case of rainbow universe, many problems related to cosmology, such as the horizon problem, can always be solved by choosing a suitable form of rainbow function. Therefore, according to equations that are produced in the framework of rainbow gravity in the structure of modified theory of gravity, an example of this equation is shown in PowerPoint page 3, and also according to explanation we provide, we perform the calculation for the logarithmic model. Various applications of the logarithmic of our gravitational model have been reviewed in the literature, such as describing neutron star as well as the Galois effect, also study the stability of the model and investigate the logarithmic form of the FR gravity model from Brain's perspective and the Planck criteria. This model has also been studied in examining a specific type of traversable wormhole with respect to various shape and redshift function. Therefore, we were able to calculate some of the most important cosmological parameters in the gravity rainbows framework for the mentioned model, including the number of efold, the tensor-to-scalar ratio, and the scalar spectral index. The measure value for such parameters are shown in PowerPoint in page 4 and 5. It is noteworthy that the numerical values can be obtained from the above solution according to observation data, such as Planck, and the number of efolding n equal 16. Also, we plot some figures as R and S by using the above equation and observable data for different values of efolding and constant parameters and n with regard to parameter of gravity rainbow lambda. In the figures, we use different n, efold, and rainbow parameters to plot the figure. Figures show the allowable range for each of them. In figure 1 and 2, we compare two important cosmological parameters R and NAS. They are relative to each other and explain the changes of these two parameters well. As shown in figure 1a, we plot the plan R NAS for n equal 2.2 and efold equal 16 as well as the various values of the rainbow parameter lambda according to the constants values. As it is clear, the allowable range of these two cosmological parameters is well shown in figure 1a. Also in figure 1b, these changes are plotted for constant parameters mentioned with a change in value of chi. So the range of this cosmological parameter is also determined if we assume the smaller value for the parameter xi, i.e. xi smaller than 50, it leads the parameter out of range. For xi greater or equal than 15, the virtual range is verified, considering the latest visible data. We also measure the changes of these two parameters in figure 2a and 2b for different values of parameter n. Of course, the valuable point is that by adjusting the parameter theta equals 0, the model is reduced to the famous Stravinsky model. In general, it can be noted that figure 1 has the most compatibility. Also, this compatibility decreases by decreasing the xi parameter and increasing parameter n. Thank you for your attention.